Hi, I'm Deriv'era. For a long time I've been thinking about doing some demo scene stuff using Amiga. Problem is I don't have Amiga, and my experience tells me to not to do demo scene without real hardware. And I don't have money to buy Amiga, not because I'm not a top developer, I just hate to work. A month ago I thought, well, I have a pack of RP2040s, but I doubt that anyone will allow it in demo party competitions, right? So why to take RP2040 seriously? But Xenium 2025, Aberration Creations, Corpse Travel was a Pika 2 or RP2350, more recent chip than RP2040, demo that was released on this demo party in Poland. It's actually big because, as far as I know, before this one, all the demos were simply just showcases. I'm not different in this. Today we will be discussing a showcase I made, not a demo scene entrance. They're much harder to make, require more direction and story, but you need to start learning somewhere, because for demo scene you need a lot of learning. The conclusion is you can make a demo using RP2040 and enter a demo party with it. And one day I wish I could try to enter some. RP2040 is definitely easier than Amiga, this is no doubt, just to be clear. But RP2040 can produce picture, and anyone can get the device, it's super cheap. This chip has limited resources, especially RAM, and that's a good fit for demo scene. I read some information on demo party restrictions and find out that you basically shouldn't attach SD card or any memory chips, you can use VGA or DVI. You apparently can use displays even if they have internal buffers. You can use external DACs to produce sound, because without it you won't be able to produce good sound. Sound I leave for future videos, let's do some VGA today. I will be using small RP2040 board with a limited amount of pins just because I find it cute. This is my prototyping board with some not connected interfaces I plan to use in the future for other projects. VGA expects analog signal with 3 different components, red, green and blue. What means analog? It means that information about intensity of the color is provided by the voltage level instead of zeros or ones. Pin of our MCU can produce a voltage level, 3.3 volts in case of the most modern MCUs like RP2040. This is only one level and you can change it using a resistor. If we combine several pins with different resistances, we actually can combine their outputs together to make different levels of voltage. 4 pins are not 4 levels of voltage but 2 in power of 4. 4 pins will give us 16 color options, because we can use different combinations of pins. With 3 color components, red, green and blue, we get 2 in power of 12 or 4096 color variants. Well, it consumed almost all pins of our board, but we mostly care here about a picture, not anything else. We left some for future sound implementation. VGA also requires vertical sync and horizontal sync signals driven by our microcontroller. They are signals to control where the new frame starts and ends, and where each line starts and ends. Timings of the signals are tied to the resolution you want to achieve. We are going to use 640 on 480 without a screen buffer, more on screen buffer later. VGA existed before the era of 16:9 screen proportions, so we will produce 4:3 signal. Even if all TVs and 60:9 monitors accepted VGA, they accepted 4:3 signal and didn't support 16:9. They usually awfully stretched the picture. I have Dell from 2007 that is 4:3 and is able to receive VGA signal. It's my daily second display. If you need to connect it to the modern screen, you can use an upscaler, if you don't want to get 4:3 screen. On AliExpress they're cheap and they produce an okayish picture. The biggest problem will be the input lag, but if you won't be gaming, it actually won't really matter. How it works and how it was made possible. I'm using VS Code with RP2040 plugin. How to effectively generate a picture using RP2040 and send it to VGA without using a screen buffer? Well, why no screen buffers? Screen buffer is a big array that contains pixels. For 12 bits per pixel you will need 2 bytes per pixel, cause 1 byte is 8 bits and you can't split it in half so easily. 640 multiplied by 480 multiplied by 2 will be around 600 kilobytes. RP2040 has only 264 kilobytes of internal RAM, so you can't physically fit such buffer. Instead, we will be generating next line of the image while sending a previous one to the screen. We will dedicate the entire second core to produce the picture. If you're seeing RP2040 for the first time, it is actually a dual-core microcontroller. To prove the concept, this is the first demo implemented, just quads flying around the screen, but there are a lot of them, and that was the first performance test for my 2D line rendering engine. We will be using DMA. DMA is a module that exists in most of microcontrollers. It moves data from one place to another. It can move data from memory to memory, but also can move data from memory to another module, like input-output, because input-output is also mapped to the memory. Or what's more important, PIO. PIO is a programmable input-output. It's hard to call it a separate CPU core, but it's close. It has its own very limited memory and is able to execute code. So you make a tiny program for it and it receives data from DMA or another source and puts it into the dedicated pins. There are a lot of limitations about this thing. For example, it is able to access only one continuous array of pins, so I need to use pins from 1 to 12 for my color output, not just random pins. And this module is very good for output tasks, well, it's called programmable input-output. RP2040 has 8 of such modules. Code for VGA, PIO I proudly borrowed from the internet. Original one is written by Hunter Adams. They implemented the most important part, timings, but they use 3 pins for color, 1 per each component. I rewrote it to use 12 pins. The code uses 3 PIOs, 1 for VSync, 1 for HSync, and 1 for color output, and they talk to each other through interrupts. Here is a table of timings for our resolution. As you can see, it sends 25 million pixels per second. It's a timing equivalent of a pixel. There are less visible pixels, of course, but we need to scale the frequency of our chip according to the 25 millions, so our pixel time will be correct. Based on this, I run RP2040 at 250 MHz. Let's move to drawing. You really want to run as many things in parallel as possible. For drawing a line into our line screen buffer, we are going to use DMA. DMA is able to use 2 bytes color as a source and just copy it into a buffer faster than our CPU can do this task. Sadly, DMA works only for flat colors and sprites without transparency, because it has no conditional blocks. All we need to do now is memorize where and what we want to draw per frame and fill the data into each line buffer when it's demanded. What happens when I do a draw call? Here I draw our quads and circles in the main loop. Information is being put into a sprite buffer. Sprite buffer accumulates all the shapes we want to draw in the next frame, but before syncing they are not visible, they are just an accumulation buffer. We have 2 buffers, so when one is rendered to the screen, the other one we fill with new data. Even if our main loop mass will somehow reduce FPS significantly, it won't break rendering. It's okay if we calculate next buffer for a long time. What is not okay if we can't calculate the next line for the screen before the previous one is sent. In this case, we will see some glitches on the screen. Quad or rectangle is pretty easy to draw. In sprite buffer I memorize vertical start pixel and vertical end pixel. By them you can fast filter what shapes belong to the current screen line. For horizontal part you simply have start and end positions. It becomes more interesting with circles. Welcome to the Deriv'era school. Take your seat, we are going to dive into the school mess. Take a look at this picture. Right, that's a right triangle. One triangle's leg is always vertical here. We know the value as the difference between middle of the circle and currently rendered screen line. Hypotenuse is our circle's radius, so second leg will be half of the circle that we need to draw. We take horizontal position of the circle and draw a line from the half of the circle to the left to the half of the circle to the right. As you can see, it works without the screen buffer. We can calculate all the values on the fly for any line of the screen. You can even draw 3D geometry without a screen buffer as well. RP2040 is capable of it. You just need to calculate triangles instead of circles. And now you have 2 circles for Yin Yang. Before we move to collisions and movement, let's discuss fractions. RP2040 has no floating point unit. It means using float, as we know them in modern programming, will be a killer for our performance. So instead of floating point, it will be a good idea to use fixed point. I define how many bits in the integer will be considered in our code as a fraction part. To make a fixed point value, you need to shift an integer left by the bits amount. To make a normal integer, you need to shift to the right. Fraction step will be 1 divided by 1 shifted left by the amount of bits, if you will need to convert it to real-world values. I mean the fraction part. Multiplication is straightforward. Just multiply two fixed point values and then shift right on the amount of fraction bits. Division is the opposite. Shift left the first number and then divide it by the second number. Maybe in the future videos I will be able to find a way to explain it better, but it's probably not a concept easy to describe in 1 minute. It needs some time to stack the idea of fixed point and how it represents fractions. I want to repeat, these are virtual numbers. For CPU they are just integers, just values, but our code and our brain treats them as something else, as a concept. There is no hardware exists for fixed point calculation. Actually it may exist, I just never heard of it, but it's something very exotic anyway. All the hardware that supports fractions is using floating point standards since 90s. How to calculate collision between a circle and a box? I assume we really want nice bouncing. I have a feeling I'm repeating this information in every video, but a box and a circle collision, it's really the most common collision detection in the game development. Take a difference between quad center and circle center and min-max both axes against half width and half height of the quad. This way you will be able to get the closest point on the quad to the circle. Now if you calculate the distance between this point and the circle's center and check it against the radius, you will know was the circle penetrated by the quad. And the difference between radius and this distance will be the penetration distance. So difference of positions of this point and the center of the circle after normalization will provide you a vector you can use to solve the collision, push circle outside of the quad by moving it along this normal on penetration distance. Also I use this vector to calculate the new direction. By randomizing the movement, I add some slight random to the new direction, otherwise movement of your balls will be deterministic. Random makes them more lively. If you enjoy my work, you can grab my game on Steam. It's a PC retro shooter I originally made for PSP, or get a PSP version on itch.io that works on real PSP. Both links are in the description. I hope you found this video educational and hopefully inspiring. I would prefer my stuff to be more inspiring than educational if you think about it. Have a lovely day and goodbye.